Chapter 2 probability from Year 2 stats is really, I would say, about problem solving. Many of the concepts you're already familiar with, but there are many kinds of difficult questions that can be asked about the topics. So just a very quick reminder of some set notation and Venn diagram notation. Given events A and B, we write A dash to mean the complement of event A. So this is the event that A doesn't happen. This is not A. A union B. So this means either A or B or both. So in a Venn diagram, the union is everything in the circles. The intersection means both A and B. So that's this overlap in a Venn diagram. Not A, the complement of A is, of course, everything that isn't in the circle A. And A given B, if we're asked about the probability of A given B, this means what is the probability that A happens given that B happens? So by definition, a formula for the probability of A given B, well, think about the Venn diagram. We know B happens, so out of all the stuff inside B, we want to know this, but only out of the stuff that's in B, so only the red out of the blue. So what is the red? The red is the probability of A and B, and the blue is the probability of B. So this is a formula you've seen before for the probability of A given B. And so this is all already familiar to you. You can be asked sometimes to find quite complicated things like this. That's not an unusual kind of question. So we'll just look at one example like that. So given that probability of A is 0.3, probability of B is 0.4, probability of A intersect B is 0.25. Part A, show that A and B are not independent. And B, given that probability of C is 0.2, A and C are mutually exclusive, and B and C are independent. The question is find probability of A intersect not B union C. Okay, so there's quite a lot going on here. First of all, recall what independent means. Independent means that the occurrence or non-occurrence of each of the events has no bearing on the occurrence or non-occurrence of the other event. Better said, probability of A times probability of B is probability of the intersection. That's what it means to be independent. So if we want to show things aren't independent, we need to show this equality in red is not true. So for part A, we're going to calculate probability of A times probability of B, which is just 0.3 times 0.4, which is 0.12. This is not equal to 0.25, which is the probability of the intersection. Therefore, A and B are not independent. Okay, part B. So we have all this information with A, B, and C. What does it mean to be mutually exclusive? That's quite important. So two events are mutually exclusive if they can't happen at the same time. So in other words, this means the probability of the intersection is 0. So this also means the probability of the union, you can add the two probabilities together. So let's draw a Venn diagram. And we know A and C are mutually exclusive. They can't happen at the same time. So there's no overlap between A and C. And then what else do we know? We know A intersect B is 0.25. We know A is 0.3, so this is 0.05. We know C is 0.2 and B is 0.4. And we know B and C are independent, so the intersection of B and C, the probability of that, we can just multiply the probabilities of B and C, which are 0.4 and 0.2, so that's 0.08, which tells us this. And then that means 0.12 has to go here, and everything in B has to add up to 0.4, so this is 0.07. And that also tells us on the outside we've got 0.43, I think. So then the probability of A intersect not B union C, well, A intersect not B is this bit in green. That's the only stuff that's in A and not in B. And then we've got union C, so then we'll do union C in yellow. So that's everything that's in C. So we just need to add everything that's shaded together, 0.05 plus 0.2, which is 0.25. Done. Okay, so that's just a quick reminder about Venn diagrams. And then I suppose we can also, we'll talk a little bit more now about conditional probability. So an important result in conditional, in fact, one of the most important results in probability altogether, in a sense, is something called Bayes' theorem. The name is, you don't need to know, but, and this goes back to the early 18th century, I think. And what it says is that the probability of A given B is the probability of B given A times the probability of A over the probability of B. And so this is, we'll call this number one. And number two, a way we can restate this if we want, is to say we can rewrite the denominator, probability of B, as probability of B given A times probability of A plus the probability of B given not A times the probability of not A. Okay, so those look quite ugly and complicated. Let's just give a proof quickly. So recall, probability of A given B, by definition, this is just the probability of the intersection over the probability of B. And then now let's think about the definition. And then let's think about probability of B given A. Again, is the probability of the intersection over the probability of A. So if we rearrange this second formula here, we've got probability of B given A, probability of A, equals probability of A intersect B. And now, if we replace the probability of A intersect B here with this thing that's underlined, we get Bayes' theorem. So we put this in here, and then we're going to get probability of A given B is the probability of B given A, probability of A, over the probability of B, QED. And then to prove the second one, we need to show, for 2, we must show the probability of B is the probability of B given A times the probability of A plus the probability of B given not A times the probability of not A. And again, you can show this directly using the definition of these two things. So Well, yeah, again, using what we just did, this thing that's underlined here is the same as probability of A intersect B. And by the same reasoning, this second thing in red is the same as probability of not A intersect B. And then if you just think about a Venn diagram for a second, A intersect B, that's this bit here, not A intersect B is this bit here. If you add those together, you get all of B. So this is, we're done. We've shown, not really good to start with what you want to show. Yeah, we've shown this expression is the probability of B, so that proves it. So proofs like this you won't have to do in the exam, it's more just for fun. But anyway, why did we do all this? Well, partly because these are useful to know later on, and also because in a tree diagram, it's really helpful to be familiar with all this stuff. Because how can we interpret this in a tree diagram? If we have an event A and an event not A, B not B, B not B, then let's think about how we label the probabilities. The probability of A we would write here, and the probability of not A we would write here. And then the question is, which probability goes here where I've written a question mark? So normally when things are independent, this would be the probability of B. So most GCSE questions, what goes here is just probability of B. But this isn't true in general because this depends on A happening. We're saying here, this particular branch is only for the case where A happens. So the probability that goes here is really the probability of B given A. So when you multiply along, you get probability of A times probability of B given A, which of course we know is the same as the probability of the intersection. And then similarly, if we go along here, this probability here is the probability of not B given A. And similarly for the others, this is probability of B given not A, this is probability of not B given not A. So and then if you think about the probability of B, the two ways to get B are either this branch or this branch. And so what we've just done, what we wrote down for number 2, these two expressions here at the beginning, these are simply what we get by multiplying these things along the two branches that give us B. So all of this kind of fits together nicely. Okay, so and it's also worth noting for independent events A and B, we also have that the probability of A given B is just probability of A, and also the probability of A given not B is just probability of A, because they're independent. So that, again, that's why if the events were independent, instead here we would just have the probability of B, where I've drawn an arrow. And yeah, likewise the other way around. This is only for independent events. Okay, so what I want to do now, oh yeah, just two more formulas you've seen before. You've seen this, which is easily justified with a Venn diagram, because this bit, which is the overlap, the intersection, we count twice when we add together the probabilities of A and B. So to only count it once to get this whole shaded red area, we need to take it away once because it's included in both A and B. Yeah, so we'll just look at a few more examples which involve problem solving in different ways. So first, let's take this. So the question is, a bag contains 5 red and 6 black counters. They are removed one at a time without replacement, and find the probability that the second counter removed is red. Okay, so we want the second counter removed to be red. There are a number of different ways you can do this. One way would be to make a tree diagram. We can either have a red counter is chosen or a black counter is chosen. So for the first counter, the black has probability 6/11, the red has probability 5/11. And then again, we either have red or black, but this time it's only out of 10. So because it's not replaced. And then we can also have the second one is black. And then again, each of the probabilities this time are only out of 10. And then if we look at there are two ways. The second one is red, that I've shown in blue. So the probability the second one is red is given by these two possibilities. It's either the 5/11 times 4/10, which is the probability they're both red, or it's and then add the probability that the first one is black and the second one is red. And then we can simplify this. This is nothing but 50 over 110, or 5/11. So that's the answer. So let's now look at another type of question. So here we have 3 people, A, B, and C, play a game that involves rolling a fair die. The first person to roll a 6 wins. And they take it in turns in the order A, B, C. And then the question is, find, firstly, the probability C wins on her first attempt. Secondly, the probability B wins on his third attempt. And part 3, the probability that A wins. Okay. Actually, on second thought, the probability A wins is going to be hard. We might just leave this as something to think about, because it's quite difficult. Because it sort of relies on some pure stuff we haven't done yet. So we might cross this out. But the other 2 parts we can certainly do. So the probability that C wins on her first attempt. Well, in order for that to happen, A and B must have rolled something other than a 6 on their goes. So the probability C wins on her first attempt, the only way this happens is if A doesn't roll 6, so we'll call that not A. B doesn't roll 6, and then C rolls a 6. So that's 5/6 times 5/6 times 1/6, which is 25 over 216. So, yeah, so you have to be careful about this. This is the way to think about it. You don't... And questions about when somebody hits a target is always this kind of reasoning. You don't want to try and make some sort of complicated tree diagram or something, because I think you're more likely to go wrong if you do that. And then now we want to find probability B wins on his third attempt. Well, for B to win on his third attempt, we would need what to happen? We'd need A not to roll a 6, B not to roll a 6, C not to roll a 6, A not to roll a 6, B not to roll a 6, C not to roll a 6, A not to roll a 6, and then finally B rolls a 6. So the probability of this, well, how many times did we not hit 6? 1, 2, 3, 4, 5, 6, 7 in a row. So that's 5/6 to the power 7 times 1/6. And then, yeah, you can use your calculator to work that out. I think I've lost my calculator, so... Oh no, here it is. So I make that 0.0465 to 4 decimal places. Okay, and by the way, part 3, just as a hint, the way to do it is you have to add up all the different ways A could win. So A could either win on the first go, or the second go, or the third go, or the fourth go, and you add them all up, and you end up with a sort of infinite series that you might be able to figure out, maybe after we've done chapter 3 of year 2 pure, what the answer is. Okay, one more example. So in a game of darts, the probability somebody hits the bullseye in the center is 0.4. The probability they hit it with one dart. So P bullseye on one go is 0.4. We want to know how many throws are necessary so that the probability of hitting the bullseye exceeds 0.9. So this is P bullseye with one dart, one go. Okay, so let's think. Well, we want the probability we hit it to be greater than 0.9. We don't specify how many times. We should say at least once. Okay, so this event, the probability of hitting it at least once, and let's say we have n throws. So we're asked to find the number of throws, so we'll call it n. The probability of hitting it at least once. The only way we don't hit it at least once is if we miss every single one of these n times. So the probability we miss every time is going to be 0.6 to the power n. So the probability that we hit it at least once is 1 minus this. Okay, and then hopefully you see the magic of this question I've invented, because we're going to have to solve this inequality. So yes, it is going to involve logs. So if we rearrange, we'll get 0.1 is greater than 0.6 to the n. And now let's take logs. So it doesn't matter what base, but log 0.1 is greater than n log 0.6, because we can bring down the n as it's a power. And then we're going to divide by log 0.6. But remember, log of something less than 1 is negative. This thing here is negative. If you divide an inequality by a negative, it flips the sign. So this greater than flips to a less than. and we have log 0.1 over log 0.6 is less than n. And then if you work this out, we get 4.507 something. So n is the least number of throws. How many throws are necessary so therefore n is 5. 5 throws are necessary to ensure the probability of hitting the bullseye at least once is greater than 0.9. Okay, we'll just, I think we might just do one final example and then we'll stop. So yeah, let's consider this this example. So we have 2 boxes of chocolates. In one box, there are 5 chocolates with hard centers and 3 with soft centers. In a different box, there are 8 boxes with hard centers and 7 boxes with soft centers. A chocolate is chosen at random from either of the 2 boxes. It is soft-centered. Find the probability it came from the first box. So, just in case it's not entirely clear, it's equally likely that it comes from either of the 2 boxes. So, a good approach is to make a tree diagram. Either it comes from the first box or the second box, and either the chocolate is hard-centered or soft-centered. So, the probability it comes from each of the boxes is a half. And then in the first box, we have 3 out of 8 are soft-centered. In the second box, 7 out of 15 are soft-centered. So the probability that it came from the first box, that it came from the first box, given that it's soft-centered, just by definition, is the probability that it comes from the first box and is soft-centered over the probability it's soft-centered. But by and, I really mean intersection, same thing. So the probability it comes from the first box and is soft-centered, well, that's this path in the tree diagram, isn't it? It's so this thing here, P, first box and soft, is a half times 3/8, which is 3/16. The probability it's soft, I'll do in blue, there are 2 paths. There's either this red path that we've already done, or it can come from the second box. So the probability it's soft is equal to the probability of the first box and soft plus the probability it comes from the second box and is soft. So this is the 3/16, the thing we've just done, plus a half times 7/15. And, okay, so that's 3/16 plus 7/30. So, yeah, we'll just work out the probability we want, which is probability of first, given it's soft-centered, is 3/16 over 3/16 plus 7/30. And then, yeah, I think probably it's just easier to use a calculator. And we obtain an answer of 45 over 101. So we're done.